Okay, so we're going to look at a geometric example of optimization again. Here we're going to look at inscribing a rectangle inside a triangle. So we'll call this optimization example. Inscribing a rectangle inside a triangle. Kind of a long title, but I can't think of a better way to describe this. And so the problem we're going to try to solve here is we want to find the dimensions of the rectangle of largest area. So clearly we're going to be looking at maximizing the area of the rectangle. Seems simple enough so far. We know how to find the area of a rectangle. So find the dimensions of the rectangle of largest area that can be inscribed in an equilateral triangle, meaning all the sides have the same length, inscribed in an equilateral triangle of side capital L. One thing to keep in mind here is that L is acting as a constant in this problem. And the idea is anything we solve for this will have L in the answer, so that if we wanted to change the size of the triangle to a different L value and plug something specific in, we could modify our answer for that particular L value. So we're going to treat this as a constant throughout the duration of this problem. So we're inscribing a rectangle in an equilateral triangle of side length L, and we want to, maximize the area of the rectangle if one side of the rectangle lies on the base of the triangle. Okay? So we need to put a rectangle inside the triangle so that one side of the rectangle lies on the base of the triangle. Okay, a lot of words there. Let's see if we can describe what's going on with a picture. And I will draw this picture over here this time. It's got to be pretty large. So I've got my equilateral triangle here, and my rectangle is inscribed inside, and one side of my rectangle lies on the base. So any rectangle I draw might look something like this. Let's pretend that's a rectangle, right? So this is our rectangle. We want to maximize the area of that, and we're asked for the dimensions of the rectangle. So maybe let's go ahead and call this length X and this length Y. Let's indicate that the lengths of the sides of the triangle are all L. And that's what we're given, okay? So what I need is I need two things. I need to know the relationship between X and Y, if I can. It will possibly involve L because L is a constant here. Like maybe L was 10, right? Don't think of it as a variable, think of it as a constant. But X and Y here can change while L stays constant, because the dimensions of this rectangle can change, and we're trying to find the dimensions that yield the maximum area. So if we're looking to solve this, we know that we're looking to minimize area, and we can describe the area of that rectangle very simply as X times Y. So no problem there. The issue comes when we try to write this function, this area function, in terms of X or Y, one variable only. And that's where we have to do a bit of work over here. So let's sort of develop an understanding here. How do x and y relate? I mean, they're just sides of a rectangle. Well, they also fit inside this triangle. So one thing we might notice is that this length down here has to also be x, which is nice because once we know that this is x, we know that these two lengths are equal, right? They're equal because of the symmetry of this equilateral triangle. And I know that this plus this has to be the total length L minus the smaller length x. I know that these two guys have to add up to L minus x, right? Because if I take L minus this piece, it leaves behind those two. So in other words, I know that this length right here is 1/2 of L minus x, and so is this over here. Now I'm going to focus on one side because both of these triangles are exactly the same. They're congruent triangles. Now, once I know one leg of this triangle, that's really helpful because there's this thing about equilateral triangles that isn't totally obvious that it's useful, but it is, and that's that we know, well, of course, this is a 90-degree angle, but we also know that this is a 60-degree angle because all three angles in an equilateral triangle are 60. They have to be equal, okay? So this is 60 degrees. And now we can get the relationship between x and y. So let's write it over here. But if I'm using some trigonometric ratios and I'm dealing with this right triangle with this acute angle of 60 degrees, I've got my opposite side and my adjacent side. I can set up a tangent ratio and say that the tangent of 60 degrees equals the opposite side y over the adjacent side 1/2 times the quantity L minus x. And the cool thing about this is this makes it very easy to solve. Let me move my y over here. This makes it very easy to solve this equation for y. In fact, if you use your calculator, the tangent of 60 degrees, if you already recognize this is a 30, 60, 90 triangle, you probably know a little bit about those. If not, depend on the trigonometry here. But the tangent of 60 degrees is just the square root of 3. So if I solve this for y, I would multiply both sides by my denominator, so I can see that y equals the square root of 3 times 1/2 is the square root of 3 over 2 times L minus x. And remember, L is a constant. So we've taken y and we've written it in terms of x. And using that thought process, I can now come back and I can rewrite my area function. So I'm just going to tack onto the side here, in case we need it later, that y is the square root of 3 over 2 times the quantity L minus x. And I'll erase our work for showing that. So I had to be creative in my diagram to find a relationship between y and x. And the way I did that was to translate x down to the bottom part of the rectangle, because then I could relate x and L, and that translated to my triangle where I knew an angle. Okay, so not at all obvious. So when you're solving these optimization problems, you really have to look for geometric, trigonometric, algebraic relationships. And that may be the hardest part of these types of problems. But now we've gotten past that. Now I can rewrite my area function in terms of one variable, and that would be x, because this turns into x times y, which is all of this. So if I distribute my x and my square root of 3 over 2, I get square root of 3 over 2L times x, right? If I distribute these two guys to the L, I get this. The reason I'm putting it in this format is because x is my variable, whereas the square root of 3 over 2 and L are constants. So I'm absorbing my constants into the coefficient of my variable x. Minus, if I distribute both of these to my negative x, I get square root of 3 over 2 as my coefficient times x squared. Okay? So now I have my area function as simple as it can get in terms of a single variable. So now I need to differentiate, find the critical numbers, and hopefully maximize this area. So differentiating this, I'm going to carry my coefficient and differentiate x just to get 1. So the derivative here just simplifies down to the coefficient, square root of 3 over 2 times L. Minus, power rule tells me to multiply my 2 by my coefficient, so I just get the square root of 3, and then times x to the, subtract 1 from the power, so x to the first power. And now I have my derivative. Once I have my derivative, I need to find the critical numbers. So I'll set this equal to 0. I'll set that equal to 0 and solve for x, right? X is my variable here, L is a constant. I know that's difficult to keep in mind. That's one of the reasons I chose to illustrate this example, in addition to the sort of curvy path you have to get get the equation in the first place. All right, so if I solve this for x, let me add the square root of 3 over x, square root of 3 times x to the right side and to the left side. And then I'll divide both sides by the square root of 3, which will just cancel this square root of 3. So x is 1/2 L, or L over 2. I don't know which one's going to be better for us at this time, but I like 1/2 L. So now we have to set up our chart. So I've got my x values, I've got my a prime, my derivative, and I've got my area function. And by the way, the smallest that x could get is 0, right? I know, in fact, x can't equal 0, so I'm going to say x is bigger than 0, but less than 1/2 L here. And on this side, x is, in fact, the biggest that x could get is L. It can't quite get there either. So on this side, I will say, well, x is bigger than 1/2 L, but it has to be less than L. Okay, so you may not catch that, but it's good for me to point out in these videos so that you're exposed to the right way of thinking as often as possible here. All right, we already know that a prime is 0 whenever x equals 1/2 L. The derivative is 0, which means that the area of the rectangle would have a horizontal tangent line if we were to graph the curve for the area function. If I plug in numbers less than 1/2 L into my a prime, then I'm going to get something smaller than the square root of 3 over 2 here, square root of 3 over 2 times L here, which is going to give me a positive number when I subtract. So my derivative is positive there, meaning that my area is increasing there. And now if I plug in numbers bigger than 1/2 L, then I'm going to be subtracting something bigger than what I started with, resulting in a negative difference. And so my area function is decreasing on this interval. And so I'm increasing horizontal tangent line and then decreasing, so I have a maximum at this x value, okay? All right, so let's go back. We need the dimensions of the rectangle. In other words, I need to know x and I need to know y. So I can erase this now. So I know that x is 1/2 L, remember L is the length of the side of the triangle, so we have to pick an x value that's equal to 1/2 L. And y is calculated using this in terms of x, so y is going to be the square root of 3 over 2 times L minus x, which is also 1/2 L. And if we simplify that, I get the square root of 3 over 2 times, well, I've got 1L minus 1/2 L gives me 1/2 L, which means that y is the square root of 3 over 4 times L. So the dimensions of my rectangle that maximize its area are 1/2 L by the square root of 3/4 L. And now what I could do is, if I wanted to know a particular value or particular dimensions in a problem like this, I could pick the size of my triangle, which is based on the L values, and I could plug those in here to find the dimensions for the corresponding rectangle with maximum area.